the Schulich School of Engineering, and this is the very first module in my computer networks video series. And I'm developing these modules as part of teaching ENEL 573, which is a fourth year undergraduate networking class at the University of Calgary. And because of that, much of the content, if you're watching this video outside of my class, maybe in another part of the world, much of the examples that I draw on in this lecture series will be very specifically Canadian. A lot of the companies that I mentioned, for example, will be companies that somebody in Alberta, Calgary would be familiar with. However, all of the networking fundamentals are very applicable to all really areas of the world today. Something else, since this is the first of the videos that you'll be watching, I should sort of explain how the videos are going to go. So as far as the format is concerned, I will be going through a series of slides. You'll always be able to see my face talking and explaining about the slides. I will sort of mark up areas of the slides as we go along. However, there will be parts of the course where we have to get into some fairly heavy mathematics, and I find it's generally not a very good idea to throw up slide after slide full of equations in front of an undergraduate class. So in the portions of the course where we do have to get into some fairly heavy math or analysis, I will actually switch from a slide format to more of a handwritten note format. And so just as a heads up for the people who are taking ENEL 573 with me, I will be providing you with the slides that I'll be showing you, but I will not be providing you with the handwritten notes. And so when you see me switching over to doing some handwritten notes, then that's your cue to pull out your paper and pencil and to start copying down those notes as well. I find that that's a little bit better way to learn than just kind of sitting there passively watching me. I suppose you could certainly print off screenshots if you didn't want to write down the actual notes, but I would really encourage you to write them down as you see them appear on the screen. Definitely pause the video if you need to sort of stop and think about something. Rewind, of course, if you need to hear something again. So that said, let's get started. So this is my very first module, and this is kind of, in a way, setting the stage. So these videos will focus very much on what we refer to as packet switch networks, or basically the internet. Much of this class is basically learning how the internet works. However, I do want to kind of set the stage a little bit and give maybe kind of almost a bit of a historical context to the material that we're going to talk about. And because of that, I'd like to start off by talking about the telephone system. So to start off, I guess if this is a class about networks, the logical question is, what exactly is a network? And I suppose a really generic definition of a network is a collection of machines or devices that are connected in some way that allows them to share information. And in a modern network like the internet, there is a huge number of different kinds of network devices. So network devices could be smartphones, laptops, Wi-Fi access points, the big Ethernet switches that you might find in a server closet in an office building or a campus. Really, it could be the thermometer in your home. So there's a very large number of possible devices. And so quite often I will use the generic term node to refer to a device in a network. And just whenever I say node, I don't want to abstract things too much, but just understand that this is basically just referring to some kind of networked computer device. And even the connections themselves in a network come in a large variety of different forms. So we can have wireless connections in a network, obviously. So the Wi-Fi connections within your home, for example. We can have wired connections internet or data communications can run through Ethernet cable, telephone lines, fiber optic cable, even through the mud that is forced down a pipe when you're drilling an oil and gas well. So there's a huge number of different kinds of connections in a network. And just to kind of give you a sense of scale for the problem facing network designers today, I thought I'd pull out a few numbers because, when I teach this course, I mean, if you're an undergraduate student in your 20s, you will never have known a life without the internet. So high-speed wireless internet has been around, and many people treat it these days almost like a utility, I guess, right? Just like, running water or electricity, we also have the internet. And, I guess maybe I don't feel super old, but I am old enough to remember kind of the dawn of the internet. And I guess I still retain some of that fascination or excitement about the internet. And so I don't think that working on network design is quite the same thing as working on regular utilities. And one of the reasons why is networks are one of the few utilities, if you want to call them that, where we are actively increasing demand. So there's a lot of push these days, around sustainability for us to use less electricity, less water, but the amount of data that we're consuming as people is growing, is still growing really considerably. And so that makes it kind of an exciting place to work. And so in 2020, the number of internet connected devices is expected to reach 31 billion. So that's a massive number. And so when you think about how to connect 31 billion devices together so they can all communicate, it's a fascinating technical problem. And one of the most high profile network devices, obviously these days, is smartphones. And we're approaching 3.5 billion smartphones in 2020. And not only are the numbers exciting, but, access to information and access to the internet is seen by many to be kind of a fundamental part of being a citizen in today's world. Back in 2016, the UN adopted a resolution recognizing internet access as a human right. And so the motivation for providing good network access to the citizens of the world really is certainly there. And that scale of problem, I believe, makes it a really interesting and exciting place to work. And I hope that excitement will kind of come across as I teach you this class, because I really enjoy teaching this course. It's really fun for me, and I really am excited about the technology. So before we dive into what the internet is all about, I do want to sort of talk about a little bit of the history of networking, if you like. And, it seems almost ancient or passé to talk about the telephone system, but I do want to take a moment to kind of honor how significant the telephone system was in kind of creating the networked society that we have today. And so it is actually a technical term, but the way that we refer to the regular telephone system is as the plain old telephone system, or POTS. And even though when you think about that, telephone sitting on a desk, it seems almost old-fashioned now. A lot of homes don't even have landline phones anymore. But even in 2013, there were 1.26 billion fixed telephone subscribers. And it really was the first communications network that connected the globe. You could pick up a phone and basically call anywhere in the world and talk to somebody literally halfway across the world. It would have been expensive. Long distance telephone calls were really pricey for much of the lifetime of the POTS network, but it was a significant achievement and really sort of set us up for realizing the internet, as you're going to see as I sort of progress through this lecture. Now, one of the technical aspects that I want to talk about for a second is the fact that we refer to POTS as a circuit switched network. And the reason why we say that is because literally when you made a telephone call on the old POTS system, when you picked up the phone and dialed that number, there was a dedicated electrical circuit put in place between your telephone and the telephone of the person you were calling to, no matter how far away it was. And we called this circuit switch because we're literally switching in a special dedicated circuit for you to make your call. And this switching was originally done by people, by operators. And so if you think about the old maybe Western movies where the actor will pick up one of those phones where you have to sort of take the handle and then you kind of crank it and you speak into the microphone kind of mounted on the wall. The first thing you would do is you would talk to the operator, who would probably be somebody in your town that you knew, and you would say, okay, well, operator, I want to talk to Fred. And literally what the operator would do would be to take a jumper cable, stick one end of it into your socket, stick the other end of it into Fred's socket, and there would be a copper wire connecting your two telephones. Now, that's the way it started. Eventually, these human operators were replaced by mechanical switches. Amplifiers were added to allow your conversation to go further. You could call between cities and countries. The mechanical switches were then eventually replaced by analog electronic switches, and then finally digital switches. Now, one of the definite advantages of this circuit switched style of network design is that the telephone system was extremely reliable. Once you switch in like a dedicated electrical circuit between two phones, there wasn't really a lot of failure in the system after that, once you were able to switch in that circuit. And so the telephone system would really boast an extremely high reliability. And the service target was literally 99.999. And that level of reliability is something known as 5 nines reliability, because there are 5 nines in 99.999. And what that means is that the telephone system was designed to provide dial tone or continuous calling capability for 99.999% of the time that it's being used. And so in 365 days of continuous telephone use, there would be about 5 minutes of downtime, which is really a remarkable engineering achievement. So now I'd like to introduce the term network topology. And network topology is basically the shape of the network when the nodes in the network and the connections between those nodes are drawn on a diagram. And so as you'll see, when we draw pictures of networks, some of them look like stars, and some of them look like lines, and some of them look like meshes. And as it turns out, the telephone system, basically, its topology was basically a series of hierarchical stars. And if we kind of discuss this a little bit, so the POTS network topology had several components, and the very first component was something called the local loop. And the local loop was the 1 or 2 twisted pair copper wires that would connect directly to a household. And these copper wires would connect to something known as the pedestal. And for those of you who live in newer neighborhoods, some of you might have those green boxes in your backyards. Not every house has them, but maybe every 4 or 5 houses have these sort of utility type boxes. And some of those boxes are the pedestals. And so basically we have a series of houses in the neighborhood, and they each all have a copper wire connected to them. at least one, sometimes two, and the two copper wires were for people who wanted two telephone numbers, basically, back in the day. And all of these local loops are connected to a pedestal. And again, these are the green boxes in your backyards. For those of you like me who live in an older neighborhood with power lines still, like overhead power lines, the pedestals are actually bundles hanging from the power lines. And so if you'll notice, these houses basically kind of form sort of a star around the pedestal. And so all of the local loop cables come into the pedestal and they get bundled together. Now we will have, in turn, a bunch of pedestals connected to nodes called service access points. And again, it's kind of a star configuration where we have several pedestals connected to each service access point. And the service access point exists basically, again, to sort of bundle those cables together into an even larger bundle. Service access points are those utility boxes that sometimes you see on street sides. In Calgary, there's often art painted on the boxes, or at least there is downtown, kind of where I live. And those are the service access points. And then finally, we have multiple service access points around the city, all connected to what we refer to as a central office, or CO. Or also sometimes COs are known as local exchanges. And so again, we have sort of a circle or a series of service access points all connected to the same central office. So you can see we sort of have, maybe it doesn't show up in the diagram I've drawn here, but we basically have a series of hierarchical stars where houses are gathered around a pedestal, pedestals are gathered around a service access point, and service access points are gathered around a central office or a local exchange. And so after things were gathered up in the central office, then the POTS network basically is, after that, divided into a hierarchy that has kind of 5 levels or 5 classes. Class 5 is the bottom level, and that's where the central offices exist. The top level is Class 1, that is known as the regional center, or RC. And an RC will then connect to other RCs to sort of connect or chain a series of telephone networks together. And that's how you can make international telephone calls, for example. Now, if we move on, it's having painted a bit of a picture of what the telephone system is like. Now it's interesting to kind of bring cable TV into the mix and start to talk about the advent of the internet and how telephone companies and cable TV companies became internet service providers. And so the telephone infrastructure, so all of this twisted pair copper wire, is owned by companies like Bell or TELUS in Alberta. And kind of in parallel to the operation of the telephone system, starting kind of in the 1970s, cable TV was invented and deployed. And until then, television was broadcast wirelessly over the air, and cable television worked by connecting coaxial cables to people's homes. And once you had the coaxial cable, generally the picture quality was much better, and you were offered a much broader range of channels. And it was companies like Rogers and Shaw that operated cable television. And for a while, cable TV and telephone coexisted. I mean, they were doing two completely different things, so they didn't really compete. But that really changed with the advent of the internet. And so I remember when the internet kind of first started, for a while, it was a little bit of a curiosity, and the people providing households with internet access were not the telephone or the cable TV companies. They were small companies. And if I think back, I think maybe the first high-speed internet modem I had was from a company called CADvision that doesn't exist anymore. TELUS bought it back in the day. But there were companies like CADvision that specialized in internet access. But it didn't take too long for both the telephone companies and the cable TV companies to recognize that the internet was going to be a thing and that they should get in on the business of providing internet access to households. And so they started to compete for the first time. TELUS would compete with Shaw, for example. And initially, the cable TV companies definitely had the advantage, and it was because of their physical infrastructure. So the bandwidth, like the amount of throughput that you can achieve over a coaxial cable, is much greater than it is over a twisted pair copper wire. And so the cable companies had a bandwidth data rate advantage to start off with. Also, initially, the only way telephone companies could provide internet service was using voice band modems. And so when you were using a modem to connect to the internet, you couldn't talk on the phone at the same time. And so either you were on the internet or you were talking on the phone, but not both. But of course, that wasn't a problem for the cable TV people because they could use their coaxial cable network. And so being able to surf the internet and talk at the same time was a novelty, and it was something that the cable TV companies could provide. However, very quickly, the telephone companies introduced digital subscriber loop, or DSL modem technology, that was able to coax more throughput out of the twisted pair copper infrastructure and be competitive, if not quite at the same level as the cable television companies. And these DSL modems also allowed you to talk on the telephone at the same time. So personally, my very first high-speed internet connection was a DSL modem that I got from CADvision, and I still remember installing it and how cool it was to be able to talk and surf the internet at the same time. So the competition didn't stop there. DSL modems were good, but they definitely had their limitations. And so the telephone company, as well as the cable TV company, but the telephone companies were a little bit more aggressive, moved very quickly to replace their copper infrastructure with fiber optic cables. And again, it was companies like TELUS that moved a little bit more aggressively because they were kind of behind the eight ball a little bit compared to the cable companies in terms of their infrastructure. And so they basically moved as quickly as they could to replace all their copper with fiber optic cable. And that's sort of the world that we're living in today. So today, fiber optic, the copper cables running to the service access points and to the pedestals have been largely replaced. And in recent years, we now have been able to have direct fiber optic service connected directly to homes. And that was a big deal. Like, I was in sort of the telecommunications research area for a long time. And at the research conferences, we would always talk about fiber to the home, fiber to the home. And then finally, when it was realized, that was a big deal because the throughput you can achieve over a fiber optic cable is enormous. And nowadays, most homes, well, all homes currently being built and most homes in newer neighborhoods do have fiber optic cables run directly to their house. If you're like me and you live in an old neighborhood with overhead power lines, I also now have fiber optic cable directly to my house because they were able to basically hang the fiber on the telephone lines or the telephone poles and kind of retrofit the neighborhood. The only houses that are still more reliant on their copper infrastructure were houses that are new enough to be in neighborhoods without power poles, but old enough that all of their underground services, like the underground wires that would have been run to their house, would have been copper. And so these are houses that were built kind of in the 80s and 90s. There's no power poles in these neighborhoods, but neither is their fiber optic cable. And in some cases, the phone companies are retrenching the fiber optic cable to these homes, but it does require either digging up your yard or using some sort of underground kind of augering sort of setup. But really, we are now largely in a world where we have fiber optic cable to the homes. And that's amazing because that fiber optic infrastructure is going to last us for decades of time. So right now, the speeds that we can get from our fiber optic cables are limited not by sort of the physics of the fiber, but by the limitations of the electronics that we're connecting to it. So we won't see an evolution beyond fiber optic cable for certainly my lifetime anyway. So now, having sort of talked about the telephone system and kind of given you a little bit of a teaser about, the internet and how the cable TVs and telephone companies have been competing, I think now I'd like to sort of move into discussing the architecture of the internet itself and how it was designed and how it came about. And as we've said, the POTS system had a sort of a hierarchical kind of star architecture. So we had a lot of kind of centralized or sort of choke points in the network. And POTS also utilized centralized control. And what that means is that there were sort of control centers that were aware of the entire sort of topology of the network and knew the locations of all the phones and all the circuits. And when calls were made, it was these kind of centralized controllers that basically switched in all of the resources to support a call. And so, as I said, the advantage of this was that it was very reliable. However, the disadvantage is that there were these very, critical single points of failure for the telephone system. And during the Cold War, people were thinking a lot about the possibility of a nuclear war, and people realized that these kind of centralized regional centers, for example, were great targets for a nuclear strike. So if you could hit a regional center with a nuclear weapon, it would take out the telephone system for a huge area of a country. And so in response to this, the American Defense Advanced Research Projects Agency, or DARPA, funded a project called the Advanced Research Projects Agency Network, or ARPANET project. And for those of you who maybe have heard Al Gore say that he invented the internet, he was actually one of the politicians who approved the funding for the ARPANET project. And the design goal of ARPANET was basically to create a decentralized network that was robust to a possible nuclear strike. So an alternative to the telephone system that wasn't quite so vulnerable from a military perspective. Now, this gave rise to, so the design goal for ARPANET was to be decentralized and not to have these sort of main, very vulnerable points in the network. And this design goal gave rise to the internet, ultimately as we know it, through a series of key innovations that were focused on achieving this goal of decentralization. So first of all, the network was all digital, so there was no, we weren't thinking about sending analog voice signals anymore. And the digital data was divided into little pieces or little chunks that they referred to as packets. And rather than sort of switching in a dedicated circuit like POTS, these packets would travel over shared infrastructure. So the infrastructure would carry a bunch of packets for many users all at once, and everybody had to share infrastructure. Nobody had dedicated resources that were assigned just for them. And finally, the packets flowed through a series of intermediate nodes that were referred to as routers. And a key innovation was that routers did not have sort of a centralized global knowledge of the network. In fact, you could plug in a router into a huge ARPANET network, and that router could figure out how to send its packets just by exchanging information with its immediate neighbors. And so just through local neighbor communication, somehow the network was able to construct a scheme that allowed packets to be sent from any node to any other node anywhere in the network. And this is one of the super cool innovations of the internet, and we're going to be looking in detail at the algorithms that make this possible. And so the result really was a self-healing, completely flexible, easy to deploy network. If you wanted to add on to the network, you plugged in a new router. You didn't have to tell any central authority that the router was there. It would just communicate with its neighbors, and that information would sort of propagate through the network. By the same token, if a router dropped out, they were thinking about nuclear strikes back then, but even just from a hardware failure, if a router drops out, the network self-heals. So the immediate neighbors for that network are aware that the router has disappeared. They then share the disappearance of that router with their neighbors, and the network learns that that is no longer a viable path for sending packets, and the packets are rerouted through a different area. Again, all of this had a military application originally, but as we're going to talk about, it was one of the things that allowed the internet to scale up. And so rather than being a circuit switch network, we refer to the ARPANET and then ultimately the internet as being a packet switched network. And rather than having a star topology, like the different layers of pots, we generally represent ARPANET and the internet as having a mesh topology. So you can think of us as having a source node. Maybe this is your smartphone that wants to post a message to a server, and a destination node that represents the server that you're trying to post the message to. And your message may initially go to your Wi-Fi access point. The Wi-Fi access point might then send it to maybe your fiber modem that you have within your home. That might go to a router that is connected to many other fiber modems. That might go to a centralized switch that has the opportunity to connect to multiple high-speed routers. This high-speed router may connect to another series of high-speed routers. This one may connect back to there. Maybe we connect to a high-speed switch in an office building, which then connects to another Ethernet switch, which ultimately connects to our server. And so because we often have multiple connections between nodes, we refer to this topology as a mesh shape. And the fundamental characteristic with a mesh is that there are potentially multiple paths for our packet to take between the source and the destination. So not initially, perhaps, we only have one Wi-Fi access point. We only have one connection to our house. This may only go to one switch kind of within, let's say, Shaw's sort of residential network architecture. But once you get into the core of the network, we do have multiple choices, particularly if the networks are traveling between cities. We can transmit a packet maybe directly to Toronto, or we could go to Seattle and then have it work its way through the United States and then make it back to Toronto. And so we have multiple paths for the packet. And the original ARPANET notion was that if one of these nodes happened to disappear for military reasons or any other reason, this node would learn about that, share that information to its neighbors, and then redirect its traffic along an alternate path. Oh, and maybe I'll draw a path there that actually works. And so how did ARPANET give rise to the internet? So ARPANET itself never I mean, it certainly grew, but it remained fundamentally a research network that connected universities to a series of government-run servers in the United States. And fortunately, we never got to learn how robust it would have been to a nuclear strike. And so how did this kind of innovative yet ultimately experimental network give rise to the internet? Well, there was a bunch of steps certainly between ARPANET and the internet, but the fundamental technical reason, and this is a technical course, so this is what we're going to be focusing on, the fundamental technical reason was the fact that ARPANET was a decentralized network. And so that means that, well, basically the success of the internet has been thanks to its ability to scale up massively. And that is a direct consequence of the fact that the internet and ARPANET originally was designed to be decentralized. So if you want to add a chunk onto the internet, you don't have to sort of update a central authority or put in a bunch of hierarchies. You can just kind of plug a router into the side of another router, and just through local message exchange, the rest of the internet learns about the little network that you've connected onto the side of it, basically. And that made the network very easy to scale up. It also made it very prone to failures. So if you were, or even just change. So if you were running the telephone network, a POTS network in a particular country, you couldn't just kind of arbitrarily reduce or eliminate a central office or an RC. You would have had to have coordinated this with all of the other people that you were connected to. And the internet, it's not quite this easy, but you can basically sort of drop out a node and then have the other nodes kind of learn about it. So you could have a bunch of people kind of working on the internet in parallel without a bunch of kind of fussy central coordination. The consequence is that the internet does not achieve 5 nines reliability like POTS used to. However, we make up for this basically with its massive connectivity. So just a little bit of terminology. So when we're dealing with networks, we often talk about LANs, MANs, and WANs. LAN is probably a term that you've already heard. LAN stands for local area network, and it refers to small networks connecting a few machines in the same sort of physical location. So we would have a LAN in an office. You would have a LAN, like the network you have in your home would be considered a LAN, for example. A metropolitan area network, or MAN, refers to a network that might cover a city or perhaps a very large campus. So the University of Calgary network would be considered a MAN. And a wide area network, or WAN, is a computer network that spans a very broad area like a province or a country. And the internet obviously would be considered a WAN. So the last topic I want to close this introductory discussion with is a discussion about network traffic. And networks are ultimately designed to carry information, and we refer to that information as traffic. And so the design problem for POTS was relatively simple. So POTS was designed to carry voice. And yes, that was eventually supplemented with technologies like fax, which somehow still live on today in our doctors and our doctors' offices and pharmacies. So people added fax onto POTS to transmit, documents. And we did for a while use it for internet access using voice band modems. However, that has largely disappeared other than, the tenacity of fax. The internet, or packet switched networks, have a dizzying number of different kinds of traffic that they need to support. And this is one of the reasons why working with networks is super interesting. So, we certainly do have voice. So there is voice over IP or VoIP technology. There are, audio only versions of, FaceTime and Skype. But largely, we have gone from, just voice specific communications over the internet to what we would call real-time multimedia communication, which of course is the video call. And I'm recording this video during COVID-19, and of course Zoom calls and video calls are just a huge part of how people are dealing with self-isolation. And so real-time multimedia communication includes Zoom, Skype, FaceTime, Google Hangouts, all that kind of stuff. In addition, we also have web and file transfer. And so this is basically transferring sort of large chunks of information at one time, like we do when we access a website. So we download a chunk of information and the website renders on our devices, and then we read the website for a while, and then if we click on a link, another chunk of information is downloaded. We could consider, social media updates to be sort of similar to this kind of traffic. We pull something off a social media server, we look at it, we push something onto a social media server. So it's sort of periodic transfers of large chunks of information. Email would be another example of this type of file transfer, or anytime we download a file to install on our computers, like an app, for example. We also have peer-to-peer file sharing, large file transfers between devices for things like BitTorrent. We have streaming video for entertainment purposes, YouTube, Netflix, Amazon Prime, Disney Plus, all of these services running over the broader internet. And we also have dedicated packet switch networks run by, for example, TELUS and Shaw to deliver sort of traditional television services to our homes. So if you have TELUS TV, for example, that appears like a separate service that isn't going over the internet, but that content is being delivered to your home using a packet switch network. And finally, a class of traffic that a lot of general consumers don't think about, but are really important, particularly for engineers, is telemetry and machine-to-machine communication. So for example, the communication between all of the sensors and controllers in a gas plant or a manufacturing facility is the majority of that technology runs on packet switch networks now, or if not, they are sort of evolving to that point as well. And so the domain of packet switch network design, the designer has to consider a whole bunch of different traffic types, which is why it makes it interesting from an engineering perspective, right? Because as engineers, we want interesting problems to solve. And finally, when we are, as network designers, thinking about how to design a network to support a particular type of traffic or a particular type of service, one of the terms that often comes up is quality of service, or QoS. And the QoS of a traffic type is basically the level of network performance required by that traffic. And so what kind of a network do we need? What does the network need to do in order to support Netflix? What does the network need to do in order to support transmission between oil and gas sensors? And when we talk about the QoS of a network traffic type, we then have a bunch of parameters that we typically kind of specify. And one of the big ones, the obvious ones, is the bit rate required by the level of service, which is typically measured in bits per second or BPS. And this is the term bit rate or throughput or bandwidth is something that is really very well known even to just kind of regular consumers, for example. Like my parents know that gigabit Ethernet is faster, or 100 gigabit Ethernet is faster than gigabit Ethernet. So we have these we literally have the throughput numbers incorporated into how we market devices to regular consumers. And the bit rate required by different applications can really vary. So HDTV, these numbers are a little old, but HDTV compressed using MPEG-2 requires between 19 and 38 megabits per second. Lower quality, older style Netflix video can run over 3 to 5 megabits per second. If you have audio only Skype, it can go as low as 128 kilobits per second. The bitrate required by a sensor in a manufacturing facility may be down in the hundreds of bits per second. So there's a very broad range of required bandwidths or throughputs depending on the type of traffic that we're dealing with. Another parameter is, well, two parameters that kind of go together are dropped packet rate and packet error rate. So drop packet rate is the percentage of packets that simply don't get delivered over the internet. And we're going to talk about all the different kind of things that can happen to a packet on its journey through the internet that cause it to be lost. We'll learn a lot about that. And we typically discuss drop packet rate in terms of the percentage of packets that are not delivered. So we'll say we've got a 2% drop packet rate, for example. Packet error rate refers to the packets that arrive but perhaps contain errors in the data that they're carrying. And, you know, again, it really depends on the application regarding how much error you can tolerate. So it's said that voice transmission over the internet can handle a packet loss or packet error rate of 5 to 10%, and we can still sort of understand what people are saying because the human brain is really good at sort of discerning audio or voice in noise. However, if we're downloading an app, for example, then not one bit in that app can be bad. The whole thing has to arrive completely intact, or we discard it. Another important parameter is latency, which is basically the delay, typically in seconds or milliseconds, that a packet experiences as it travels over the internet. And this is particularly interesting in the domain of video calls, for example. I read an interesting article just recently about Zoom and how Zoom has a design goal of less than 150 milliseconds of latency or delay in their video calls. And that seems like incredibly fast because I think it takes about 200 milliseconds to blink your eyelid. But studies have shown that delays on the order of 300 milliseconds start to disrupt a natural flow of conversation. People will start to interrupt each other by accident. Studies have done also showing that the credibility of a speaker is degraded as delay is added between a question being asked and a response. So for example, a study was done where the test question was, can you give me a ride home from work? And the answer was sure. And as more delay was added between the question and the answer, the people participating in the studies would consistently rate the speaker as being less credible because they had to sort of wait before they said sure in response to the question. And so delays of tenths of seconds make a difference when designing networks. And jitter is a related parameter, which is variations in network latency. And so we're going to explore all of these parameters. And basically the purpose of this class is to look at how to build a packet switch network in order to meet the QoS requirements for a variety of different traffic. And we're going to see that there actually is there's often very interesting trade-offs. So for example, we can make a very noisy error-prone channel or link between nodes appear error-free, but we pay a penalty in the effective throughput or bandwidth that we would achieve over that link. And when these types of trade-offs arise, that's interesting from an engineering perspective, because finding the right balance between competing parameters is really a lot of what engineering is all about.